Hey guys, and welcome to day 4 of our online learning. So this is day 4 because this is the 4th day that I would have seen you if we had been in just regular school, okay? So we're going to go over a couple things, including a short lecture by me before diving on into today's assignment. So just a couple of things. If you are not checking Home Access Center, you should be doing that often. You should also be checking your email, perhaps once a day. You can also get your email on your phone. You can also get Google Classroom on your phone. And I would recommend doing that and then just ignoring them after like 5 p.m., which is what I do. A couple things. So the stream on Google Classroom has a couple of reminders of just how class is going to go. On Friday, for example, we will not be having an assignment. Instead, I will be hosting a Google Meet for you to join. Here's the link right here if you are interested. And we can kind of just pop in during this time. Oh, and here's my cat, sorry. And getting the extra help on assignments. Okay, let's look at this. Oh my goodness. Okay, hi everyone, this is my cat. He will be perching here for a while. Okay. So a couple of things about the assignment from Monday and Tuesday, the temperature versus time graph. So if you look at these, each day we'll be having either a discussion that you have in Google Classroom or else some sort of exit ticket. This is your attendance assignment. This is how I know if you are here. These shouldn't take you but 5 to maybe 10 minutes to answer. There are a couple of reflection questions about the unit and also a question about how you're doing and how are things and just getting some extra interaction in, okay? I'll continue posting the slides and updating them as we go along, okay? Then your assignment and then the video. The video should be the first thing that you watch as I explain both what the assignment is and what you need to do for it. Our temperature and time graphs. A lot of us perhaps made the mistake, I'm going to say, and give you guys the benefit of the doubt. I got a lot of assignments that have just the data on them, but we're missing the actual graph, which was kind of the whole point, right? Like if I just wanted data, then I just would have told you to make up 10 numbers for me. So make sure that your assignment has the graph on it, as well as 1 to 2 sentences describing the trend that you see. If you, for instance, are missing an assignment, then that doesn't mean that it is done with. So if this is your attendance for the day, then this is the grade that goes in the grade book, okay? So for example, the one that we'll do today, this is how I know that you were here. This is how I give you a grade. So if, for example, I don't know, perhaps you're working on the assignment, you get this done, and then something comes up, or you're sharing internet with 4 other people in your house, or all of a sudden you have to go to your part-time job. Then you can complete this later, and I'll just give you some feedback. Hey, I haven't received this yet. And as soon as you get that in, then I can update your grade. So don't feel like if you have an N or a 0 in the grade book from an assignment, you can't complete it after it was due. It is still good to go ahead and complete these things so I can update your guys' grades. Okay? All right, let's go ahead and dive right in on our lesson. We'll start here. All right. So the first thing to do, of course, is to listen to the videos. Go ahead and complete this Google form. You should be able to do that using information that you have from the videos, as well as just like a little reflection piece. Yeah. And then after that, today we are going to do an online lab, and I'm going to show you guys how to do this, essentially. All right. So today's topic, as it will be going forward for about 3 or so weeks, is going to be energy, and we're just going to go over some things. So guys, we're not going to go super into doing the equations in this class that will be more reserved for both chemistry and physics. However, we will probably use kinetic energy and potential energy equation, okay? And then I put these here, work and power, just in case. I'll refer back to these. I will post the equation next to a problem if I have you solve it. But I just want to get us a little bit familiar with those and to have a slide in which you have all of the equations present. All right, so a couple terms. It's going to be fun. So if you remember from our forces unit, then we talked about what a force is. A force is some mass. I'm going to use my little pin jar here as my example, that I accelerate, right? I move it, and I don't just move it, but it actually speeds up or slows down or changes direction. That's a force. So the force that I exert on this sort of green pin holder is describing what is happening to the object, right? To the thing holding my pins. I'm putting a force in. I am moving this mass and I am accelerating it. Now, work isn't necessarily concerned about the object. It's more concerned about what I'm doing. That's important too. So work is the ability to put a force on an object and move it a certain distance. Work is measured in joules, but we also sometimes measure it in, guess what? Calories. Yeah. So work is actually pretty synonymous with energy. In fact, energy is the ability to do work. That's how you know something has energy. A couple quick things that sometimes are a little confusing. Work doesn't happen if you don't move something, no matter how much strain it feels that you're doing. So if you are lifting weights in the gym and you put too much on it and you are not able to lift the bar at all when you're doing like a chest press, then according to physics, you haven't really done any work, right? You haven't lifted it yet. As soon as you lift it against gravity, though, even if it doesn't move upwards at all, then you are combating the force pulling down on something as you kind of lift up. And that counts as doing work. If you're able to move the bar at all upwards, then you have done even more work and you have put energy into something. For example, I'm moving soon. So if I am trying to move my fridge, let's say, and I push and push, but I'm not actually able to move it, then I have not put work in. No matter how sort of exhausted I feel afterwards. All right. So that's what work is. Work is force multiplied by a distance. The force is measured in newtons and the distance is measured in meters. Okay, moving on. A system. A system is anything in which you can imagine a boundary. Systems can be as small or as large as you need them to be, but they're determined by what you want to know. So say you want to know how much electricity your house uses. And the system is your house and everything in it that uses electricity. It doesn't matter how much electricity your neighbor uses because the system is just your house. Say you want to know how long it takes for a certain wave to travel across the galaxy. Then your system is the whole entire galaxy, and we're not concerned with anything outside of that. If you want to know about something really, really small, like what's happening to an object as it's placed on a table, or even what's happening to a cell inside your body, then that cell or that table becomes your system. So the system is just anything of which you need to study what's happening to the energy inside of it, and you're not concerned with anything outside of it. Most of our systems going forward for energy are going to be pretty small, but not cellular small. They're going to be just, hey, here's an object as it falls from the tree. The system that you are concerned with is just the small area around the tree, not necessarily the whole park or the whole forest or even the whole city. Okay? All right, energy. Energy is a difficult thing to describe, right? We all know sort of what it is. We know what gives us energy. We know what it takes to do something, that things cost energy. But we don't necessarily have a good definition for what energy itself is, because energy is not a thing. It's not something that I can reach out and touch or grab or experience with my senses. Energy is the ability to cause some type of change in a system, just at its most basic, or it's the ability to do work. Work is how we transfer energy. And if we think even about energy in different forms, like if we talk about solar energy, which is where most of our energy on Earth comes from, or if we talk about chemical energy, then which we take in through food and then break down and perform into mechanical types of energy, the ability to actually move our bodies and for our bodies to function, then all of these different types of energy are just work that is done within that system, however small or large, whether it's the whole Earth or whether it's just you as like an organism. So energy is ability to do work. Keep that one. Okay. Typically, when we talk about energy, we sort of use it interchangeably with the idea of power, but these are not quite the same thing. So power is how quickly energy changes or work is actually done. Power is measured in watts, which you might remember from just talking about electrical objects or our electricity unit, right? Whenever we're talking about power, we're not necessarily describing how much energy has. We're talking about how efficient that object is. So efficiency is related to how capable you are of doing something in a certain amount of time, maybe. Power isn't really concerned about things having the same amount of energy. They're worried about things that can do work in a certain period of time. So here's my example. Let's say I have two UPS workers. They both have the same task. They have to move 100 boxes in 8 hours in a normal workday. One worker moves all 100 boxes in an hour. He has just like set a record, right? Another worker takes 5 hours to move the boxes, which is still a pretty great frame of time. Both workers have done the same amount of work. They have moved the same mass, they have accelerated it over the same distance, and they have done this, so same force, same distance, same acceleration. Everything checks out there. So they have done the same amount of work. They've moved the same amount of stuff, and it took the same force in order to do that. However, one worker did it in a shorter amount of time than the other. So the difference between power and work is that power is dependent upon the time that it takes to accomplish something. So power is only related to time. Work can be done anytime, whenever need be. Okay, and our last thing. So today's exercise, today's online lab is over potential and kinetic energy. And so I'm just going to go over these quick ideas real quick, and then we're done for the day. So there's two main types of energy. There's kinetic and there is potential. And then there's a small offshoot of kinetic. So kinetic energy is the energy of an object because it has motion, because it is moving. So things that move, vehicles, animals, ourselves, also molecules, right? So there's a little bit of kinetic energy in molecules as they bounce around the room, and that's called thermal energy. So your guys' check-in question asked you about what heat is, and heat is a measure of temperature for sure, but heat is also related to just how fast particles are moving inside of something. If it's hot, they're moving very fast. If it's colder, then they're not moving as fast. The thermal energy related to heat, again, is the sum of all the kinetic and all the potential energy in an object. And we're going to get into how that describes the three laws of thermodynamics next week. All right, so that's kinetic energy. Kinetic energy is pretty easy to understand. People understand, hey, if I need to eat a big breakfast, maybe not a big breakfast, a good breakfast though, in order to do some type of sport or some type of physical activity, then I need energy in order to move. I need energy in order to do kinetic things. Potential energy is a little bit harder to describe. Potential energy is the energy an object has or can store based upon its position. So it has to do with position. The number one type of potential energy that we're going to talk the most about is gravitational. So it takes energy just to hold yourself up above a height against gravity. It takes energy just to walk around because you are having to fight against gravity. This kind of energy is highest when an object is standing still but is hovering above the ground. So this is the common book drop as an example. A teacher holds a book. Don't have a book. I just have this pen. I don't want to go grab a book. Okay. I hold this pen up high, and as I hold it, it's not moving. So all of its energy in the pen is potential. It has the potential to fall to the ground. It is doing, or I'd say I am doing, work against gravity to hold it up. I'm using energy right now to hold this pen up. Not a lot, but energy. Now, if I let it fall to the ground, right, then as it fell, it converted some of this potential energy as it fell into kinetic energy. And it did that because it was losing height, but it was gaining velocity from gravity. So my example here is gravitational energy would be like a sled on a hill. Elastic energy is another type that we're going to not talk as much about, but this is the energy that is stored when you either compress or stretch out an object. So one example is a bow and arrow. Even before you release the arrow, that string is kind of taut, right? It's kind of tight. And that has energy and the ability to push that arrow a great distance. If you have ever hit somebody with a rubber band or used a slingshot, or I don't know about you guys, but I used to have really, really small ponytail holders that my mom would put in my hair when I was very, very little. And if you ever had one of those snap against your head, then it is a very particular type of pain that I am never going to get over. And those things, those elastic things, the things that can stretch, those have elastic potential energy. Before they hit something, whether it is a person across the room or my very, very tender head, then it has energy stored in it before it snaps. All right, the last type that we're going to talk about is chemical energy. And we're just going to kind of define this one. We're not going to deal with it too much because we talk about it a lot more, obviously, in chemistry. But chemical energy is the energy stored because chemicals are bonded together, right? Because atoms are bonded together and they form bonds. They either break those bonds or they form new ones. An example of this is the food that you eat. You take in chemical energy, which used to be technically solar energy, right? The food that you have was either grown because it was a plant and it was grown through sunlight, or it was an animal that maybe ate a plant, like a cow, or it was an animal that ate another animal that ate a cow. Somewhere along those lines, the base of all this is sunlight. That's the source of all the energy on our planet. That sunlight is used to grow your food. You eat your food, you break down chemical energy, you take that energy and you perform all of your bodily functions, most of which are mechanical in nature, unless you do kinetic energy, and also to produce some thermal. All right, please go ahead and watch this video of this astronaut. He does a really great job describing how these things apply, a little bit in space, but also just in general, and it's a pretty short little video. Also, this one. This is all the energy on this planet. these things will pop back up, I promise. Okay, and real quick, because I know you were curious, how to use this equation. Today I'm just going to talk about the potential energy equation, and I'll introduce the kinetic energy one next time. Potential energy is equal to the mass of an object multiplied by the acceleration of gravity. Gravity is measured at 10 meters per second squared, and we talked about how it affected everything that fell with the same acceleration. These two things are multiplied by height. Height is measured in meters. So if you have these three pieces of information, the mass, the acceleration of gravity, which you should always have, it's always 10, and the height, then you can figure out how much potential energy an object has. So if I have a mass of, let's say, 10 kilograms, just to keep it easy, and I lift that 1 meter above the ground, then I would take, and let's see if I can do this here. Okay, oh, nice. Then I would take my 10 times the 10 of gravity, and then times, I think I said 1 meter, right? The 1 meter, and I would get 10 times 10, that's 100. 100 times 1 is still 100. And I would get 100 joules of energy. So in order to lift up 100 joules, in order to lift up this object 1 meter, it takes 100 joules of energy. That is the potential energy stored in that object. Okay? Now, for your assignment, what I'd like you to do, let's go ahead and click to the pointer, is go here. Okay, please make sure you're bolding your answers. You do that by writing your answers, highlighting them, clicking the bold button. Thank you. Here's a quick reminder of different types of energy, the ones to refer to, please. Kinetic energy is often written Ke or big E, like subscript K. It's a common thing. Potential energy, Pe. If it's due just to gravity, then it'll either say E for energy and then a little G next to it. There should be a G involved if they're talking about gravity. That's what you need to know. Thermal, it's just therm, or TH sometimes. All right, what you're going to do is go here to the SPET lab on energy skate parks. We're going to, oops. Okay. Get rid of that one. That should pop up. You're going to check a couple things, the bar graph, the pie graph, and speed. And we're going to start off on the intro, okay? So I'm going to move this back. Okay. So intro. So pie chart, bar graph, speed. Don't worry about the grid. If you don't click all of these, you don't necessarily see it. And let's just kind of play around with this guy. All right, so you can pause it. And let's look at this. So he's got a medium speed. He has a lot of kinetic energy. That makes sense, right? Because he's moving. He has a skateboard. He is moving. And we see that almost all of the total energy of my skateboarder is due to kinetic energy. Okay, let's let him go a little bit. Ooh, pause it there. All right, now we see, okay, so he's still moving, right? There's still a little bit of the green of the kinetic energy. You can see it here too. So I like how this shows you both ways, in the pie chart, shaped like a pie, and also in the bar graph. Okay, so his potential energy, though, is most of his energy. Here's total energy. Notice this hasn't really changed. This height has not changed. However, these two are going to fluctuate. And yeah, so almost all of his energy is due to potential energy because all of his energy is stored in that position that he has above the ground. He now has the ability to fall and go faster. So we see, aha. All right, if you just watch over here too, you'll notice that these two things change position. Now the other main question is, why is he still going, right? Why isn't he slowing down? The thing that slows us down is friction, which I can activate. If I go back, then there's like a second one where we can activate friction, and that would give us thermal energy. So if you have ever skidded across the concrete on your bike, then you know that some surfaces are rougher than others. We are saying that this surface is frictionless, which means this person is going to go on forever unless friction is high enough to slow them down. So kinetic and potential are just changing places, and they would do that for literally all of time until this person either jumps off, decides to stop, or if friction was high enough on this particular ramp in order to slow them down. Okay. That is it for the day. You can sort of play with it a little bit if you want to. Make different shapes here. Follow these instructions. Make sure you are answering them in either complete sentences or just explaining your reasoning, please. That's probably the biggest key here. And with that, you guys have a great night, and let me know if you have any questions on either on my office hours, just email me, comment on the assignment, that helps a lot, or if you would like to check in Google Meet and just pop in and say hi, get some help real quick, okay? Have a nice night.